Today, we will be showing you how to estimate the area under a function using the left and right hand approximations. Let us begin with showing you how these approximations work.
We can estimate the area under the function through the use of rectangles and trapezoids. In this example, we're using rectangles. We can add up the areas of these rectangles to create an approximation of the area under the graph.
Here we have the function f of x equal to x squared. So now to start this left-hand approximation, we'll draw in the rectangles.
The width of the rectangles is determined by something called the step size. Here, we're working with the interval 0 through 4. We divide this interval into subintervals, and here we're dividing into 4 subintervals, and each of those subintervals is 1 unit, length long.
The height of these rectangles is determined by the value of the function on the left-hand endpoint, hence the name left-hand approximation. So here, we take a function of 1, which is 1 squared. So the height of this is 1. Here, it's the function of 2 squared, so that would be 4. And then here, likewise, 3 squared is 9.
And since the base of all these rectangles is 1, we know that the area is successively 0, 1, 4, and 9. We can add them up to get 14, and therefore we know that the left-hand approximation of f of x equals x squared gives us an approximation of 14 on the interval 0 through 4.
So now let's try the same graph, except with a right-hand approximation. Alright, so now we're going to be working with the same function on the same step size and over the same interval, except now we're going to be using the right-hand approximation. So we'll be drawing the rectangles.
The only difference between the right-hand approximation and the left-hand approximation is that in the right-hand approximation, we use the right endpoint of each subinterval as the height of our rectangles.
So here, as you can clearly see, we have rectangles with the heights 1 squared 1, 2 squared 2, or 2 squared 4, my apologies, 3 squared 9, and 4 squared 16.
Again, in order to find the right-hand approximation, we have to add up the areas of these rectangles. 16 plus 9 plus 4 plus 1 gives us 30. Therefore, the right-hand approximation of f of x equals x squared over the interval 0 through 4 with a step size of 1 equals 30.
So now let's try something a bit more difficult, the trapezoidal approximation.
For trapezoidal approximation, we once again divide our interval into subintervals with the width determined by our step size, which is 1. Now, each subinterval becomes, and its width becomes the height of our trapezoid. The different bases of our trapezoid is determined by the height of the function at each endpoint of the subinterval.
So as you can see here with these 4 trapezoids, the various bases of the trapezoid will be for the first one 0 and 1, for the second one 1 and 4, for the third 4 and 9, and for the fourth 9 and 16. And as you can see here, the trapezoids are a lot closer to an approximation than either the left or right hand approximations.
Now, once again, we add up the areas of the trapezoids in approximation. And in order to find the area of the trapezoid, we use the basic formula 1/2 times height times the sum of base 1 and base 2. Therefore, in this case, we get the first trapezoid to be 1/2,
the second to be 5 halves,
the third trapezoid to be 13 halves,
and the final and fourth trapezoid to be 25 halves.
and the sum of them is 44 halves, which is also 22. Therefore, we can say that the trapezoidal approximation over the subinterval of 0 through 4 with a step size of 1 gives us the approximation 22.
In review, we had our left-hand approximation for the function, right-hand approximation, 30, and our trapezoidal approximation, which was 22. So now, let's test the accuracy of these approximations using the integral. So first, we're going to integrate over the interval 0 to 4, which was the interval that we calculated the approximation for of the function, which was x squared. Using basic antidifferentiation, we can deduce that this equals to 1/3 x cubed from the interval 0 to 4. Now, plugging in the values 0 to 4, we have 1/3 times 4 cubed minus 1/3 times 0 cubed. Since this final term is just 0, we can just cancel that out. And so we figure out that the integral from 0 to 4 of x squared is 64 thirds, which is equal to 21.3%.
As you might have already noticed, the trapezoidal approximation is clearly the closest to the true area under the curve. However, we also notice that the left-hand approximation is less than the true area under the curve, and the right-hand approximation is greater than the true area under the curve. Now let's investigate why this is. The left-hand approximation can either be greater than or less than the actual area under the graph. Now let's investigate in what cases this can happen. Here we have an increasing graph and a decreasing graph. On the increasing graph, if I start to draw the left-hand approximation, I can clearly see the left-hand approximation is less than the actual area under the graph. On the other hand, on the decreasing graph, if I start to draw in the left-hand approximation, we can see that it's clearly greater than the actual area under the graph. Now why is this? As we look at the increasing graph, we can see that the left endpoint will always be lower than the right endpoint. Therefore, the area that we approximate under the graph will always be less. On the other hand, in the decreasing graph, the left endpoint is always greater than the right endpoint. Therefore, the approximation will always be greater than the actual area under the graph.
Similarly, there are two cases in which the right-hand approximation can either be greater than or less than the actual area. Like Karthik described, there are both increasing and decreasing cases. In increasing, we draw the right-hand rectangles as such. We can clearly see that they are greater, but then, on the other hand, decreasing will be smaller. And for the same reason that Karthik talked about earlier, is on the increasing function, the right-hand endpoint will always be greater than the left-hand endpoint. So you will always have this extra space here. So therefore your area that you approximate will be greater. But for decreasing, there will always be this left uncovered, so to speak, because the right-hand endpoint is always lower than the left-hand endpoint. Therefore you get a lower area approximation for the decreasing function with the right-hand. Something you'll find with the trapezoidal approximation that you won't find with either the left hand or the right hand is the fact that it really doesn't matter whether or not the function is increasing or decreasing over the interval. Rather, it becomes a question of concavity to determine whether or not the approximation is greater than or less than the actual area.
Now let's examine a concave up curve. I'm going to draw in an arbitrary trapezoidal approximation on this curve. Now watch closely. As we can see, visually, the approximation is greater than the actual area of the curve due to this extra area that the trapezoidal approximation creates.
Now we'll examine a concave down function. Once again using the arbitrary trapezoids as such. You can see that there is some area that is left uncovered by the trapezoid, which would be in here and in here. Now this is as a result of the function being concave down, and therefore you can conclude that when the function is concave down, your approximation will be lower than the actual area.
Thanks for tuning in for today's lesson.
Be sure to stay watching for someone else's video, which is probably better than ours.
I don't know what happens next.